Very good morning to all of you. In the last class, I discussed you regarding the calculation, regarding the derivation part of two compartmental open model if the drug will follows your IV bolus administration. Right? In that, we learned about the method of residuals. And one more method, mass balance equation. Mass balance equation for deriving two compartmental open model of your IV bolus administered drug. So after deriving all these things, we need to assess the PK parameters if our drug will follows two compartmental open model when the drug has given through IV bolus administration. So the next one is assessment of PK parameters. So the parameters of K21, K12 and Ke. So here we are talking only about the drug deposition parameters which will be transported between the two compartments. Okay, you always remember this chart in your mind. So here we are assessing K12 constant parameter, K21 as a parameter, and after that the most important one, elimination. This phenomenon was carried out from your central compartment. So for that reason there is a assessment between K12, K21 and Ke. Ke is nothing but your K13. It can be derived by proper substitution. So these three equations are written directly. There is no derivation part. So how you can remember these three equations? Okay. See, previously what we have seen, we have derived this equation from our method of residuals. In that we had two types of hybrid constants. Those are capital A and capital B. These two are called as hybrids. So which hybrids these two are? Exponential forms. These two are exponents hybrids. Exponents hybrids. I already told you many times while discussing this two compartment open model. Here we need to get two deposition processes. Those are distribution and elimination. So for that reason we can able to get two exponential forms for this deposition processes. What are the two exponentials here? E to the power of minus alpha t and e to the power of minus beta t. So here first exponential form of e to the power of minus alpha t, the hybrid constant is capital A. For this e to the power of minus beta t, the hybrid constant is capital B. So what do you mean by capital A and capital B? Here I am writing capital A because here we will get the distribution deposition process 1, that is capital A, that will represents you e to the power of minus alpha t. Simple thing. In this capital B, here we are considering terminal elimination part here. This graph terminal elimination part. So this capital B is representing us e to the power of minus beta t exponential form. With this concept, you can write these equations very easily. See, this is Ke, nothing but K13. So from which compartment we can able to get the elimination process, that is from one compartment to the third compartment, nothing but K13. Okay, it is looking like capital B. So nothing but your elimination rate constant. Here you have to write alpha beta. So for this elimination, there is an involvement of distribution. What is the distribution exponent constant? Alpha. Next, then beta. This is elimination exponent constant. And C naught. This is the initial plasma drug concentration. From initial plasma drug concentration to the terminal phase of elimination, there is an involvement of excretion process. From initial, that is at 0, 1, 2, 3, 4, like that. These all are belongs to the time points. Okay, so here we can take concentration point. So from 0 to infinity, so from T0 to infinity, the drug will be traveled on n times, right? So in that cases, here our elimination should involve from concentration 0 to the infinity. So at which point it is going to be start, then we will consider as C naught. C initial. Plasma drug concentration initial, C naught. Then it is divided by A. A represents you the alpha exponential form, right? But here we can multiply this A with beta and B with alpha. So we can multiply with opposite terms. See, A is nothing but e to the power of minus alpha t. B is nothing but e to the power of minus beta t. So here we are writing capital A hybrid constant with the exponential form, distribution exponential form, that is A into alpha, A into beta, A into beta, B into alpha. See, A into beta plus B into alpha. So here you can able to get elimination rate constant. Then the next parameter is K12. Here our drug is distributed from central to the peripheral. A, B, within the brackets B minus alpha. Okay, so beta minus alpha. Beta is nothing but B minus A whole square. This is whole square. B minus alpha whole square divided by C0 A beta plus B alpha. When you add these two exponential forms hybrid constants, we can able to get how much amount or how much concentration of the drug should be present between these two compartments. So that's why here we are adding to get proper amount of drug distribution within the K12 constant, K12 compartments, that is central to the peripheral. And the next one is, here it is somewhat different. See, K2 to 1. That means your drug is from peripheral to the central. K2 to 1. Right? So, K2 to 1. Here, there is no involvement of elimination processes. See, directly you can write A beta plus B alpha. So here no need to write any minuses and any multiplications here. Why? So if the drug is transported between the peripheral to the central, the peripheral compartment is not playing any role for the drug elimination. Only the central compartment is eliminating out our drug. So for that reason, here we are not writing anything. See, only we are writing C naught. So here we are considering only the initial plasma drug concentration with respect to the deposition hybrid constant and elimination hybrid constant. Ke is the elimination of drug from the central compartment and rate constant for elimination from entire body. And overall elimination T half can be calculated from beta. So next parameter AUC. AUC means area under the curve, right? So this is called AUC. This is whole area which is available for drug absorption is nothing but our area under the curve. When you take the time here, when you take the concentration here. So how we will get this area? Here we have alpha and here we have beta. Alpha is nothing but capital A and beta is nothing but capital B. See, A divided by alpha plus B divided by beta. Okay, if you know this graph in your mind, it is easy to write. So, A divided by alpha plus B divided by beta. Then you will get how much amount of the area available for your drug absorption or drug processes. Then the next parameter is VD. So what is the equation for calculating volume of distribution? Here we are always talking about central and peripheral compartment. So there is a need to calculate the VD separately for central and peripheral. For central VD calculation, we can write it as VDC. That is volume of distribution in central compartment. In case of peripheral, VDP, volume of distribution in peripheral compartment. So we already know the relationship of X is equals to VD into C. Then VD is equals to X by C. We already know this relationship. Amount of the drug, concentration of the drug, volume of distribution. Then here VDC, volume of the distribution in central compartment, X naught by C naught. Here we are taking initial amount of the drug available, initial plasma drug concentration. Then you will get X naught, initial amount of the drug. Instead of writing C naught, you can write Ke into AUC. So here initial plasma drug concentration is also available under this AUC curve. This is the initial. So your curve gets starting from here. This is the 0 time point and 0 concentration point. So from this 0, the drug will get eliminating out slowly. From this 0, it will get eliminating very slowly. At this point, you can achieve 100% elimination, ma'am. At this point, you can get 1, 2, 2, 2, 2, 3. If time is processing, you will get some low limits of elimination processes. For that reason, there is a need to consider your elimination process also to calculating the initial plasma drug concentration. So how you will get initial plasma drug concentration here? By taking consideration into elimination and AUC. So the VDC is X naught by Ke into AUC. And the apparent VD for peripheral compartment. See, here VDP is VC. So here the drug is being transported from peripheral to the central. It is a reversible, no? So then here we have 2, 1. Here we have 1, 2. So then for calculating volume of distribution in the peripheral compartment, so we have to know the volume for this central compartment also. So this VC is volume of central compartment. Volume of central compartment into constants K12 divided by K21. So for requiring to calculation of VD for peripheral, so you can take consideration into central, but you want to calculate VD for central, you are not taking consideration into peripheral, because this from this central only all these mechanisms are going on. And then for calculating this central, it is a major compartment for doing all possible physiological physiological phenomenon. For calculating the central compartment volume of distribution, we can take initial plasma concentration, initial amount of the drug, along with this AUC. For calculating VD for P, only we are taking consideration into VC, volume for central compartment, and the rate constants which are traveling reversibly to one compartment to the two to one. So that's why the reactions came like this. Then apparent volume of distribution at steady state, or else it is also called as equilibrium. So here we are taking C and P, 1 and 2. So at steady state point, there is a need to add these two volumes, that is VC plus VP, volume of central compartment and volume of peripheral. Here we can get individually, okay, volume of central and volume of peripheral. So then we have to add these two volumes, then we will get volume of distribution at steady state. This can also written as VD area is equals to X naught divided by beta into AUC. Here we are considering only the elimination exponent. Whenever beta will comes, elimination will comes in your mind. Then distribution means you have to remember alpha and capital A. Elimination, beta and capital B. Then this is VDSS. SS is steady state, volume of distribution. Then total systemic clearance. What is the denotation for total systemic clearance? CLT. So this is equals beta into VD, that is elimination exponent into volume of distribution. So these PK parameters can also be calculated using the urinary excretion data. Whenever this urinary excretion data will comes, you can remember it XU. U stands for urinary excretion. Small u, capital X, small u. U stands for urinary excretion. X means amount. So whenever you can calculate this rate of change in the amount through urinary excretion, the equation is dxu by dt. This is rate of change through urinary excretion. Then K small e. See here, till now we have seen only K capital E. I already told you K capital E is there and small e is there, right? K capital E is elimination. So elimination includes metabolism and excretion. But K small e is only for excretion. Here there is no involvement of metabolism. K small e, excretion rate constant. So when you can calculate this urinary excretion rate constant, that is dxu by dt, definitely Ke will comes. Ke is excretion rate constant into volume of central compartment. Here excretion we will get it from only central compartment. That's why we can write here Vc. Then the renal clearance, KLR stands for renal clearance, Ke into Vc. So this dxu by dt is nothing but your renal clearance. So this is all about two compartmental open model IV bolus. Okay, IV bolus administration of a drug. In your syllabus of 4th unit, you have two compartmental open model, then IV bolus administration, then IV infusion and extravascular. Till now, we finished only two compartmental open model and IV bolus administration. The next one is IV infusion. Okay, so IV infusion, here also involvement of central to the peripheral compartment, the drug will be transported. Here you can get two different concentrations. Then here you have elimination rate constant. Okay, then The plasma or central compartment concentration of a drug that fits in two compartments. See ma, the plasma or central compartment, the concentration of a drug that will fits in two compartment when you can administered at a constant rate. Here why we are telling constant rate? Tell me. Here we are talking about infusion. So how the transportation of drug will be takes in case of infusion? The rate constant, sorry, the drug will be transported at a constant rate, because here the drug will be slowly absorbed, right? In case of IV bolus, how the drug administration will be? Very rapidly absorbed. And in case of IV infusion, the drug will be slowly absorbed. That's why here we are telling about constant rate. So this constant rate will follows you the zero order, right? So this can be given. So here there is no derivations. You can directly learn this equation. So from where we will get this equation? In the previous IV bolus administration, we have a equation. See here. Once again, I will show you this slide. Okay. So here we have capital A and capital B values like this. Okay. So for writing IV infusion, you can remember these two equations. Then it is easy. Okay. This is a one exponential hybrid rate constant. This is other exponential hybrid rate constant. So from these equations, we will get this equation. See, at steady state. So here, in case of two compartmental open model, we can't say at which point the steady state was happened. So that's why here we are considering the time alpha. The drug is transported from time 0 to time infinity. Sorry, time 0 to time infinity. So that's why at steady state, the time is infinity. The second term and the third term becomes 0. That means this is the third term and this is the second term in these equations. This is the first term. So at steady state, the time is infinity, the second term and the third term becomes 0. Then the above equation becomes, so if it is 0, 0 plus 0, 0, 1 plus 0, 1, and R0 divided by VC into KE into 1 is equals R0 divided by VC into KE. See, CSS is equals to R0 by VC into KE. Here we are talking about steady state plasma concentration. Now VC into KE is equals to VC into KE is equals to VD into beta. Very simple ma. CSS is equals to R0 divided by VD into beta. VD into beta is nothing but your total clearance. And one more important thing, I had a doubt. Why R0 here? This is nothing but infusion rate. Infusion rate, that is R0. So you just remember what we studied in one compartment open model, then you have to applicable here. You have to apply here, right? So R0 is infusion rate constant. The loading dose X0L is obtained CSS immediately at the start of infusion. So how you can calculate the CSS? CSS into VC, volume of central, is equals to R0 by KE. This is a very small IV infusion derivation for the drug follows two compartmental open model. Okay, this is about IV infusion, and you have only one more part in your fourth unit, extravascular administration. Extravascular is also called as oral administration of your drug. Okay, so see ma'am, whenever you are going to calculate your extravascular administration or oral administration, there is a need to calculate Ka. Okay, in case of IV bolus, there is no Ka. Why? Because we are selecting only rapidly absorbed drugs. Then why we should add this Ka? There is no absorption, zero absorption in IV bolus. And in case of IV infusion, we have a infusion rate at steady state, that is zero order. See the differences. And in case of extravascular or oral administration, we have a Ka. Ka is nothing but the absorption rate constant. Is it clear? Then this absorption rate constant, first it is going to central, then we have peripheral. So then we have the same mechanism K12, K21, and here we have elimination from central compartment. Here only one difference is absorption rate constant because it is following extravascular administration. Okay. The drugs enters into the body by a first order absorption distribution according to the two compartmental open model, the rate of change in the drug concentration. So here also we are considering only the central compartment, right? So the rate of change in the drug concentration that is in the central compartment can be described by three exponents. Okay. Are you remember or not? While starting this two compartmental open model, I told you if the drug will have two exponents or three exponents or n number of exponents. In case of two exponents, we will get it in IV bolus. In case of this extravascular administration, we have three exponents. When we want to calculate this change in the drug concentration in the central compartment can be described by three exponents. What are those? Capital N is one hybrid constant, capital L is other, and capital M. Here why we have three exponents? It is also very simple. Because of this absorption, we have one more exponent. See here, e to the power of minus KAT, e to the power of minus alpha t, and e to the power of minus beta t. We have e to the power of minus alpha t and minus beta t in case of IV bolus. But in case of extravascular, we have an absorption rate constant. That's why we have Ka, that is absorption rate constant, e to the power of minus KAT. So here we have N, L, M as a hybrid constants for respective three exponential forms. It is very simple. So only one thing you have to learn this graph. So N, L, M, we have three hybrid rate constants, right? So how we will get this graph? See, when we will plot T versus log C. T versus log C. Firstly, we will get the graph like this. This graph will show you the slope of minus alpha by 2.303. So your alpha, you see here, the slope is minus alpha by 2.303. So when you extrapolate this straight line to this curve, you can able to get log m values, Then this is the first curve. The second curve will also be happened like this. So up to this mark, the graph will be straight. After that, the graph is changing its shape. So from this, you can get the slope as beta by 2.303. Here the slope is alpha by 2.303 and here the slope is beta by 2.303. From this changing of its shape, you can extrapolate the line to this x-axis. See, then you will get log L values. Then how you will get log N values? Same like yesterday's graph. Method of residuals, I already explained you one graph. So when you extrapolate the graph from this y-axis to the x-axis, you can get a slope Ka. This is absorption rate constant. Only one thing you have to remember here, we need to get three slopes. Why? Because here we are using three exponentials. These exponential constants are L, M and N. So log L, log M, log N. So how you will get these values? By drawing this graph. So when you back extrapolate the distribution curves, log C minus C bar, we already know how we will get this back extrapolated plasma drug concentration. So one is true plasma drug concentration value and the second one is back extrapolated distribution curve, and the third one is back extrapolated elimination curve. Finally, it will first residual curves, that is log CR values. Here you have second residual curves log CR2 values. It is very simple. Okay. So this is a semi-log plot of C versus T of a drug which is following two compartment characteristics when it will be administered extravascularly. So the various exponents have been resolved by the method of residuals. See, the three exponents can be resolved by stepwise application of method of residual assuming Ka is greater than alpha greater than beta. Besides the method of residuals, Ka, your absorption rate constant, can also be estimated by Lou-Riegelmann method for a drug that follows two compartment characteristics. Okay, so apart from this method of residual, your absorption rate can also calculated by Lou-Riegelmann method. This method requires plasma drug concentration time data for both oral and IV administration. See, whenever we are doing calculations in our lab, DPPK lab, then you can able to get clear idea how we can calculate this absorption rate constant using method of residuals or using Lou-Riegelmann method. We have number of calculations in our lab. Okay, so in the theory part, you can remember up to this mark. So this completes your total unit number 4, multi-compartment open model.